Hi, my name is Samir Desai, and in this video, I'm going to teach you how to predict the major product of a keto-enol tautomerization reaction.
Before jumping right into predicting a product, we'll build on the foundational concepts so we can understand the why behind tautomerization reactions. Aldehydes and ketones are structures that are talked about frequently in organic chemistry. These functional groups can be identified by their carbonyl group, a carbon double bonded to an oxygen. The general formula of an aldehyde is the carbonyl bonded to a hydrogen and an R group, where the R represents a hydrocarbon substituent. A ketone is very similar and can be written with the carbonyl bonded to two R groups on either side of the carbon. Now, on both of these carbonyls, there is a very important hydrogen that allows the tautomerization to occur. The hydrogens are on the R groups, so I'll just draw one hydrogen on this aldehyde and one on this ketone. Both of these hydrogens are attached to an alpha carbon, which is the carbon adjacent to the carbonyl carbon. These hydrogens are slightly acidic because the conjugate base is stabilized through delocalized electrons of a double bond. This is important because the weakly acidic hydrogen is easily deprotonated, so the aldehyde and ketone exist as isomers in a solution. The aldehyde would exist in solution as an isomer, where only the hydrogen and double bond differ in placement. So the structure would still look a lot like the aldehyde, but now the hydrogen would be attached to the oxygen and the double bond shifted between the two carbons. Similarly, the ketone would look like the following isomer, again with the double bond between two carbons and the hydrogen now bonded to the oxygen. Now, in keto-enol tautomerization, the aldehyde and the ketone are referred to as the keto form, and the enol refers to the other isomer. A double bonded carbon is an alkene, so the ene provides the prefix of the enol, and the OH is the alcohol, which provides the suffix OL. Tautomers reference the keto and enol form, so the conversion of a keto to an enol or an enol to a keto is called tautomerization or enolization. The keto form is more stable, so the equilibrium arrows would actually look like this, with a longer arrow towards the keto isomer, and a shorter arrow like this towards the enol, to represent more keto than enol in a solution. Now, there are exceptions to this rule. With phenol groups, the enol will be favored because the aromatic rings contain delocalized pi electrons, which creates resonance that is much more stable than a keto group. Additionally, an enol with internal hydrogen bonding will create stability as well and favor the enol. Let's take a look at some practice questions and not only predict the product of tautomerization reactions, but also determine which tautomer will be favored. As discussed before, tautomerization occurs because a hydrogen attached to an alpha carbon is weakly acidic and can be deprotonated. In A, the carbonyl carbon is here, but notice there are no adjacent alpha carbons. This methanol cannot be deprotonated as it contains no alpha hydrogens. Therefore, there is no enol formed and no reaction. Moving on to B, we see the carbonyl carbon here. Therefore, there are alpha carbons on either side. Since the alpha carbons are both equivalent, regardless if the hydrogen deprotonated, the stereochemistry will be the same. So we'll assume this hydrogen will get deprotonated. The enol tautomer will have a similar structure, but the hydrogen will be bonded to the oxygen and the double bond will now be between the carbons. This enol is neither a phenol nor does it have internal hydrogen bonding, so the molecule will favor the ketone. C looks similar to B, but notice there are some double bonds within the ring. The alpha hydrogen on the less substituted alpha carbon here will be deprotonated, so we'll see an enol that looks similar to the ketone, but with the hydrogen and double bond shifted to create a phenol. The enol form is favored with phenols due to aromatic stabilization. Lastly, D. The alpha hydrogen between the two carbonyls is more acidic than a typical alpha hydrogen and is very easily removed. The enol form would have the same structure, but with the hydrogen and a double bond in a different placement. This molecule has internal hydrogen bonding between the hydrogen on the alcohol and the carbonyl oxygen, resulting in a more stable enol compared to the keto group. Now you should feel comfortable predicting the major product of a keto-enol tautomerization reaction.